friends, today I'd like to talk about the fundamental limit of trigonometry and its application with the L'Hopital. So the recent trend in the exam is that they put emphasis on the L'Hopital with the trig identity, but things can go rabbit hole unless you do some simplification in the algebra. So let's see how we can overcome those problems. But without further ado, let's get started. There is a revision video in my YouTube channel, and in there, what I also specified when I was briefly going over the limit is that you must know this fundamental limit of trigonometry. There are three versions of it, right? The sine theta over theta, the tangent theta over theta, and arctangent theta over theta. When you send theta to 0, they all converge to 1, and being able to prove them could be assessed in paper 3. So in the video, what I also talked about here is that so the first thing is the fundamental limit of trigonometry, and then the second thing is that you need to do algebra, right? Before we do the L'Hopital many times, simplifying the limit really helps, because it's not really about it's not about checking your differentiation skills. It's about whether you can simplify things algebraically, especially with the trig identity. So bearing those two things in mind, let's try to tackle several problems. So the very first thing I want to show you here is that the fundamental limit of trigonometry can be seen especially with the proof of the sine, of the derivative of a sine. So, the first thing that you do with the derivative of a sine is that you want to associate with the first principle. So let's try to plug into the sine function there. And then, as you can see, if I put 0 in the limit, I get 0 over 0, right? And that often we associate this as a indeterminate form. And if you have indeterminate form, what you want to do is really try to use algebra to simplify. For example, if I have a limit x goes to 2 of x squared minus 4 over x minus 2, let's say, then of course if I plug the 2, then it becomes 0 over 0, then it becomes indeterminate. I don't like it. And for the polynomial form, I know I can factorize using the difference of a square. For example, on the top, that means I can actually factorize, right? So if I did, it's going to be x plus 2, x minus 2 over x plus 2. So that's brilliant, because I can cancel things out, right? So then if you send x to 2, it will simply become 4. So yes, whenever you have indeterminate form, you can do the L'Hopital, but if you could do the algebra, that's the best kind, and I do strongly recommend to try to simplify as much as you can. So on this one, for the sine, right, what sort of algebra can you do? Well, there are several approaches, but what I recommend is that every time you have the difference of a sine, what this reminds me of working with the sum to product. So here, if I remind you, sine, A minus sine B using the sum to product formula can be plugged into 2 cosine A plus B over 2 sine A minus B over 2. Right, so that's what I can have. That's the sum to product formula. And here, if I apply the sum to product formula for you, this is the ratio I've got. And then if I simplify further inside by just doing the division, because here I got the 2x over 2, so that will be just simply x, and this is what I have. And from here, what I want you to realize is that I can actually send these two to the denominator by 1 over 2, so it's going to be h over 2. It's just the reciprocal, isn't it? Reciprocal of it. Reciprocal will be on the numerator, so it's gonna be 2 here. And then this actually reminds you of the fundamental limit of trigonometry. Please remember, limit theta goes to 0 of a sine theta over theta by the fundamental limit of trigonometry is actually going to be 1. So this actually converges to 1. So now if you send h to 0, it would be simply 0, so then limit here becomes simply just 1 times cosine x. Hence the derivative of sine, I can say that it's gonna be cosine x. Remember, this limit here becomes 1. But one thing I want to remind you here, please remember the limit. For example, x goes to 0, sine 2x over x ain't 1. Please be careful, because the period and the denominator has to be the same. The rate must be the same for the gradient, meaning you want to make sure that I put the same number, same input and the denominator. So if I had a 2x there, what I would do arbitrarily is to make this as a 2x, but I didn't have it before, did I? So I'm going to multiply by his reciprocal again, so that the ratio becomes the same with the rate, and that will converge to 1. So then here the limit will become 2, is what I can tell you. Okay, so make sure the input and then the denominator must match to claim that the limit is going to be 1. Right, so that's something that I want to remind you about the fundamental limit of trigonometry. So let's have a look at the next problem. In the next problem, it says, without using the L'Hopital, let's try to find the limit of the arctangent 2x over tangent 3x. Okay, so this was the exam question before in the recent year, but they did ask you to use L'Hopital. But I just want to show you it becomes really convenient if you know the fundamental limit of trigonometry, and hence you use it right here. And for this one, what I would ask you to do is always arbitrarily try to match the input with the denominator. For example, for the arctangent 2x, what do you want to put the denominator as? You're absolutely right. I want to put the denominator as a 2x. And for the tangent 3x here, my friend, I'm going to match with the 3x so that the ratio is the same, right? So 3x and 3x, I'm very happy, right? And then here, I didn't have a 3 over 2 before, where x cancels out sort of. So I'm going to multiply their reciprocal, which is 2 over 3. Oh wow, that's great. And now by using the fundamental limit of trigonometry, we saw that the arctangent theta over theta, when theta goes to 0, becomes 1. So I can just say that this actually goes to 1, this goes to 1, so hence the ratio will be simply just the 2 over 3. But of course, if the question demands you to use the L'Hopital, you got to use it. But if it didn't ask you to, you could still manage using the fundamental limit of trigonometry. That's the convenience of it, right? So now let's have a look at the next problem, right? And for the next limit, here, I got the sine squared kx over x squared, okay? And then what I'm given here is a limit of 16, But as soon as I noticed that, oh, okay, that looks really, really similar to the fundamental limit of trigonometry, I'll be very happy. I'll be very joyful. Because I can use the sine theta over theta as long as I match the input, the kx, as well as the denominator, kx. So I got this sine squared kx over x squared. I'm very happy. And here, what I like to do is to make sure the denominator is the same. But right now, I got the x squared, so I got the x and x. I just please realize for the perfect square I decomposed, right? But now I want to match the denominator as the input k. So what I can do is arbitrarily put the k in the denominator, but make sure I didn't have it before. I could still claim this to be k, but essentially it needs to be the 1. So I got to multiply by their reciprocal, which then becomes the product of k and k, becoming the k squared. Oh wow, then by the fundamental limit of trigonometry, this limit, the theta over theta is the same ratio, same rate, will just become 1. So in fact, the limit just becomes a k squared. And that k squared happens to be the 16, and k, they asked me to the positive real, so I'm going to result the k to be just simply 4. Right? So I don't need to do the L'Hopital. You could, but you notice that it's going to be, it has to be done twice because I don't like working with the x squared. If you send x to 0, so denominator is always the bad boy. But now you realize it's gonna be the chain rule, and either you can do the product rule or use the double angle of a sine to simplify things, etc., etc. But why not just do it right away, realizing that as soon as I see that sort of a sine theta over theta, I would like to use the fundamental limit of trigonometry. So that realization for the L'Hopital is super important every time you see something with the trick, and then the question demands you to use the L'Hopital. All right, let's have a look at next very messy problem, seemingly, right? That now I got to find the limit of h goes to 0, and the numerator has got the secant 4, the power 4, and I got the cosine square, and I got the x squared 4 minus x squared, right? So x to the power 4 minus x squared, and that looks very demanding. Well, first of all, I like to check whether it's eligible to find the limit, and for that, the good start is to determine whether it's indeterminate or not. So if you put x equal to 0, secant 0 is a 1 over cosine 0, so cosine 0 is a 1. So I got the 1 minus 1 over 0 minus 0. So I got the 0 over 0, so it's indeterminate form. Brilliant. Okay, so it is subject to L'Hopital per se. But by inspection, if you check this out, I don't really feel the urge of doing the L'Hopital there, because the differentiation of a secant power 4 is humongous, right? So if I have a secant, for example, x to the power 4, and I gotta differentiate, I will have to do the chain rule, right? So it's gonna be 4 secant cubic x times, what is it going to be? It's gonna be secant x times tangent x. So that makes it what? 4 secant 4x times tangent x is what we get. And I really don't want to get into the rabbit hole of that, because as you can see, if you still put the x equal to 0, it becomes a 0. So I got to do the L'Hopital once again, and for that I got to do the product rule and a chain rule once again, and it gives me a headache. Okay, so for me, what I like to do is try to reduce as much as possible to use the algebra, and then try to see which one is the problem for this limit to make it indeterminate form, and then find the limit for that. What do I mean by that? Let's check it out. So you know what, for me, it gives me a lot of simplification because of even power, right? I'm able to factorize as much. So let's try to check out the numerator first. I got the secant to the power 4 minus cosine square, where you know it's probably better to make it into the equal term. So I got to make it into the cosine to the power 4 in the denominator for the reciprocal trick. And then I put it into the common denominator. Then I got the cosine to the power 4 in the denominator, and the numerator to be 1 minus cosine to the power 6. All right, so that's great. And maybe I can, so now for whatever the limit I had before, this is the limit now I've got, because I replaced the difference of that power 4 square as the ratio of the 1 minus cosine to the power 6 over cosine to the power 4, okay? But for me, it doesn't really look obvious, right? It looks still very challenging, okay? Therefore, I would perform more factorization. Remember, for the L'Hopital problem, for the indeterminate limit, it's all about the simplification, whether you can do the algebra to factorize and cancel out. So for the next limit here, so I got this form here, right? And there are more rooms to factorize. For example, obvious factorization is going to be the denominator with the even power. And then I got the also difference of a square there too. If I put the cosine cubic x, cosine to the power of 6 as the square of the cosine cubic, I can do the difference of the square too. So let's check it out. For that one, I just did the difference of a square. I hope this is obvious. And then, in fact, you can also factorize the difference of cube too. So this is what the quotient we had before. So I factorized that way. And for the, denominator here, the common factor was x squared. So then it's going to be x squared minus 1. And I can do the difference of the square here also. So that's how I've got this, okay? And then next step that I'm going to do is actually to factorize the difference of cube too. Because difference of cube, I want you to please remember a cube minus b cube. So that's a minus b, a squared plus ab plus b squared, right? So that's what I have. That's the difference of cube. That's the expected algebra for solving this problem more neatly. So I got that factorization. That's great. And now, if you try to send, for example, the limit x to 0 for this one, right? And let's see who's the bad boy. Okay, so who's the problem? So, well, first of all, if you put 0 here, it simply just becomes 3 because cosine 0 is simply just a 1, isn't it? So then he's not going to be the problem. The problem is actually the ratio of the 1 minus cosine x and then the x squared, right? Because if you look at that, that makes everything indeterminate form because 1 minus cosine x, when x tends to 0, it will become 0. And x squared becomes 0 when x tends to 0 as well. So now I'm going to focus on this limit in particular, not everything else, but just this ratio here. Because that makes everything really complicated because this is the fundamental indeterminate form. All right, so this is what I have. And on this one, I like to do the algebra. Well, before we do the algebra, let me show you the simpler one. So yes, as you have said then, because it's an indeterminate form, I can do the L'Hopital, right? So let's try to differentiate top and bottom. If you differentiate the negative cosine x, it becomes a sine x. Derivative of x squared is simply just 2x. So now, I don't need to do the L'Hopital because I got the sine x over x. That is essentially the fundamental limit of trigonometry, which we know it will converge to 1 as x goes to 0. So I got the half. So that's the limit for that, right? So that's the L'Hopital on that limit after having reduced only the essence of the limit that I need to find. Anything else is actually defined, right? But let me try to use this, try to define this limit without using L'Hopital. Imagine that I didn't know the derivative of a cosine. How can I still find the limit just using the fundamental limit of trigonometry? Because this one used L'Hopital once, right? Let me try to actually evaluate this limit without using the L'Hopital. So what you can do here is every time you're mixed the cosine with plus minus 1, you really want to get rid of it, right? So how we can get rid of the 1 is to use the double angle of a cosine. So, well, it's not in the multiple of 2, you may say, so I don't have a double angle. Well, we can make it because cosine x is simply just cosine 2 times x over 2, right? And here I'm going to subtract the cosine with 1, so I really want to get the positive 1 from there. And to do so, what you can remember here is maybe I will use the 1 minus 2 sine squared x over 2, which is one of the double angle of the cosine. For which then, if you subtract, the 1 cancels out, the negative 2 becomes double negative, so I got the positive 2 sine squared x over 2. I'm very happy with that, okay? And now I got that similar ratio of the sine square of the x squared. That really that demands me to use the fundamental limit of trigonometry. Well, let's try to make it same. So what I've just done for you, so we got that limit here. And from there, what I like to do is to put the 2 in the denominator. I got that. But realize it's a perfect square, right? So I would decompose again, sine x over 2 times sine x over 2, just like that. And then as you know, the ratio must be the same. The rate must be the same. I got the x over 2 here. I got to have x over 2 there. So unfortunately, for the second one, it's not perfectly the fundamental limit of trigonometry because I don't have x over 2. So I need to put the x over 2 here arbitrarily. But don't get me wrong, you shouldn't change the limit here. So you got to still multiply by its reciprocal so that it's going to be essentially the same limit. Right? But now realizing that this is actually matching each of them. Now it matches each of them to claim that this is going to be the fundamental limit of trigonometry because the sine theta over theta will converge to 1 as theta goes to 0. Okay? Thanks to the fundamental limit of trigonometry. So that this will converge to 1. This will converge to 1. So 1 times 1 times half, it will end up being just half as well. So for the limit that we started with for this question, still doesn't require the L'Hopital if you are very familiar with the trigonometry, and this is absolutely fine. Okay, so now let's try to put all the information here. So I got the 1 minus cosine cubic x of x squared, which I've tried to do this in the, the difference of a cube, and then we realize this limit, we just proved it using either L'Hopital or without, that it converges to half. And then the other cosine value, if you put 0, that becomes just a 1 and 1, so that's just 3, so it becomes 3 over 2. Brilliant, no problem. And now, therefore, let's try to go to the factorization of this limit here. We managed to put everything in terms of a cosine after having changed this into 1 over cosine to the power of 1 and put it into common denominator, no problem. And we actually managed to factorize this even further. And now, okay, the limit that we had to be careful to make this everything indeterminate was this highlighted ratio, which we saw that it converges to half. So this converges to, so that converges to 3 over 2, right? We just proved it above. Okay, so that's great. And then let's try to put x equal to 0 on the rest of the function. So now here, if I put x equal to 0, will simply become 2, all right? And this will simply just become 1. This will become 1. This will become negative 1. So the ratio, the denominator will be simply just negative 1. And now multiplying the 2 by 3 over 2, so it cancels out. So the limit will eventually be 3 over negative 1, which will be simply just negative 3. So the logic here is as soon as I see the, this treacherous limit here, I'd really be reluctant to differentiate, because think about it, to the power of, you can obviously do it. I hope you realize the trend of this optimizing as a differentiation problem these days has been really focused on the derivative of the sine. Trig, either right angle, reciprocal, inverse. They've been asking you a lot of heavy algebra with the trig ratio. Remember the optimization problem, like around the corner, I believe, like a corridor like that, and you wanted to sort of rotate this thing around, and for that you had to use a lot of cosecant and secant, and the question asks you to find like the minimum or maximum length of it, and for that it's extensive algebra with the trig ratio, right? And then such as this problem, you could have done this with the heavy algebra of the derivative of sine, but I wouldn't have, because as you can see, I can simply solve this using just algebra with the trig as well as the fundamental limit of trigonometry. So here's my tip for you. Please memorize, okay, 2 things, all right? What you have to memorize is the what you really want to memorize, my friend, is that the first thing, right, the sine theta over theta, or tangent theta over theta, or arctangent theta over theta, they all converge to 1. But not only that, I ask you to I demand you to know why. Right? Why do they converge to 1 without using differentiation? Only by squeeze theorem. Okay, by sandwich theorem, if you get to know why they actually converge to 1 using the sandwich theorem, will be brilliant. And for that, you need a very, very important inequality in trigonometry, which is given as the following. And I want you to please realize that this inequality appeared many, many times in the IB exam. So make sure you know how to derive this inequality and then use it for finding the limit of such functions, okay? But yeah, that's the end of the video today. I wanted to show you L'Hopital is not about always differentiating 3 times and 4 times. You can do it once or twice, but if it gets more than that, I will stop. And then I will ask myself if I can use algebra to simplify things and then work on it. Okie dokie? But yeah, that's pretty much it for me today. I will see you next time. Thank you.